Hello and welcome back. So this video is for class 12 and we will continue with chapter 7 alternating current. So previously we saw the concept of impedance, okay, in an LCR circuit. Now these concepts, all the concepts that we saw till now, they are very important. Just ensure that you have seen the previous videos and you have understood the topics. Today let us move with the next concepts. The first concept we will see, that is the concept of resonant frequency. Okay, now this concept will be applied in an LCR circuit. So we have a normal series LCR circuit. In that circuit, the maximum current, the peak current will be given by Im is equal to Vm upon Z. And of course we know what is Z. Z is nothing but the impedance, that is Vm upon under root of R square plus Xc minus XL square. Again, I am sure you remember, but Xc, that is the capacitive reactance, XL, that is the inductive reactance. Okay, so imagine we are having a series LCR circuit where the peak current is given by this relation. Now you can go on alternating the frequency, okay, the frequency of the AC supply. At some frequency you will see that the Xc, that is capacitive reactance, becomes equal to the inductive reactance. And of course such a thing is very much possible. Okay, so if you go on changing the frequency, at some point you will get Xc equal to XL, right? So if Xc becomes equal to XL, what will happen here? Xc minus XL will become 0 and we will get the maximum value of the current, because this impedance will become the lowest. So what will happen in that case? In that case we will get Im is equal to Vm upon R square under root of R square, that is nothing but R. So we will get Im is equal to Vm upon R, that is the maximum value. So when you get the resonant frequency, okay, so resonant frequency, that frequency at which Xc becomes equal to XL, or we can say omega L becomes equal to 1 upon omega C. Okay, so this frequency at which this is taking place is termed as resonant frequency. Okay, we can write this as omega equal to 1 upon under root of LC. So this term is given a subscript of 0, okay, naught, that is, and then omega naught we call as the resonant frequency. Then how much is the resonant frequency? Resonant frequency is equal to 1 upon under root LC. Okay, and what happens at resonant frequency? We get the maximum value of the current, which is given by Im equal to Vm upon R. Next we will talk about the concept of LC oscillations. Okay, LC standing for inductor and capacitor. So here we have a capacitor and an inductor. They are connected to each other. There is no power supply here. Okay, initially let us imagine the circuit is open and we are going to charge our capacitor. So let us say we have given it some amount of charge. Let us say Qm. Okay, that is the maximum charge that we have filled on our capacitor. The circuit is open, so nothing happens to the charge. Then what we will do? We will close the circuit. The moment we close the circuit, what will happen is the charge will begin to flow. Let us call these points as A and B. Right. So what will happen? The charge starts to flow and it goes from A to B. And of course that is nothing but the electric current. Okay. So we get an electric current flowing through our circuit. Okay. And this sets up something called as the LC oscillations. What happens is the charge starts to flow from here. It is going from A to B. As it is going through the inductor, it is going to store some energy in the inductor as well. It is going to produce some EMF due to the self-induction. At one point what will happen is the charge on this plates of the capacitor will become balanced. So no, it is not going to have any energy. Okay. But now what the inductor will do, the inductor will come into place because it has got the potential energy. It will push the charges and it will charge the capacitor. But what it will do? It will change the polarity. Means earlier this plate was positive, this plate was negative. The inductor, what it will do? It will charge this plate and make this as positive, the other plate becomes negative. Once this happens, again now the current will start to flow in the opposite direction, that is from B to A. And this will keep on happening. These are termed as LC oscillations. Now of course you will say, is this a practical concept or a theoretical concept? This is a theoretical concept. Because in real life, if you connect a capacitor and an inductor, there are going to be many losses, because we don't have any inductor that is having zero resistance. It does tend to have some amount of resistance, so we don't get perfect oscillations like this. But in terms of theory, let us say if you have an inductor that is having no resistance at all, okay, and all the conditions are perfect, there is no dissipation of any kind of energy, then we will actually get these perfect kind of oscillations. But for now, let us do the derivation. So let us say at some time t, the charge is q on the capacitor. Okay, so we can get the relation by using the Kirchhoff's loop rule. Q by C minus L di by dt equal to 0. Now this relation, will remember we have done it previously also. Okay, we are basically using the Kirchhoff's loop rule. So you get Q by C minus L di by dt equal to 0. Let me call this equation number 1. Now what is this I? I is the current. We will write current equal to minus dq by dt. Why this minus sign is being written? What you will see is, as the charge will decrease, the current will increase. Is that correct? Because this Q shows the charge that is stored on our capacitor. That is why this minus sign is being shown over here. Okay. So because we are seeing an inverse relation, charge जैसे कम होगा वैसा current बढ़ेगा. Okay. So as the charge will decrease, the current increases. So you have to put this minus sign. So using this relation in equation number 1, we will get this equation 1 as Q by C plus L d by dt, and here I will write dq by dt equal to 0. Correct. Now this term, as you can see, d by dt into dq by dt, the square function we will get. So we get the relation, and we are going to rearrange it just now. L d square q by dt square plus q by c equal to 0. Now let us divide the entire relation by L. So we divide it by L, so this L gets cancelled, and here we get L into C equal to 0. So we get the relation d square q by dt square plus q by L C equal to 0. And if you observe, this equation shows a simple harmonic motion. So here is the relation we got. What we got? We got d square q by dt square plus 1 by LC into Q equal to 0. And as you said, this is representing a simple harmonic motion in this form. D square x by dt square plus omega naught square into x equal to 0. Correct? This omega naught square is nothing but the resonant frequency, which is equal to 1 by LC. So once again, from this relation you can see that omega naught is equal to 1 by under root of LC. So here we are seeing the LC oscillations into place. Okay. So because they follow this relation, we are seeing simple harmonic oscillations. But once again, I will tell you, this is a theoretical concept. When we try to do it in practical life, we don't get so perfect oscillations. But if we were to get perfect oscillations, they will keep on happening. That is, the capacitor would charge the inductor would charge the capacitor, and they would keep doing it, and that is why we call them as the LC oscillations. Now, how much would be the energy stored in these LC oscillations? The energy stored would be only stored by the capacitor. Okay, and how much energy is stored by the capacitor? It is 1/2 Qm square by C. This Qm is nothing but the maximum value of charge that the capacitor can hold. So during LC oscillation, in an LC circuit holds energy equal to 1/2 Qm square by C. Okay, this relation also you have to remember. Next, let us discuss the concept of transformers. Now, transformers also you must have heard many times. We are having in our areas the current that we are getting. Okay, it passes through these transformers. The reason that alternating current became so popular is because alternating current can be used in transformers. Now, what are these transformers? Okay, as the name suggests, they transform something. But what do they transform? They transform the voltage. So let us say we are having a power station. Power station will create a very high value of voltage. Let us say it creates a voltage of 20,000 volts. Now it has to create a very high voltage because that current has to be sent a very long way, right? So it creates a voltage of 20,000 volts. But if that is the amount of current we are getting in our households, that will create a lot of problems. It might prove to be very dangerous. So what is done? We use something called as a step down transformer. Means the current at 20,000 volt is transported to some distance. Then a transformer cuts that voltage into half. So 20,000 volts, we cut it into half, we get 10,000 volts. Then again that current goes to some distance. Again we have a step down transformer, it cuts the voltage into half. And that is basically the function of a transformer. Because of these transformers, by the time the current is reaching our house, it is up to 220 volts. Okay, because we use a series of step down transformers, right? So that is the main function of transformers, and this is what we are going to see in this topic now. So basically for transformers we need two coils. One we call as a primary coil, the other we call as a secondary coil. So here we have one coil. Okay, let us call it P, that is the primary coil. There will be another coil that we will call as the coil S, that is secondary coil. Now of course you will remember this diagram. Okay, we have talked about that if we pass an alternating current in P, there will be induced EMF in coil S, and that is where we will get our current to go through. Okay, so we can basically transfer by electromagnetic induction, we can transfer the current. So it is the same thing. Okay, so you can have two coils which are either separated by some distance, or for transformers you can have coils one over the other. Means we can have a primary coil, and on that same coil we could have the secondary coil. Okay, so both these are possible. So anyways, so we have a primary coil that we have called as P. This primary coil is having number of turns NP. Okay, NP is the total number of turns in the primary coil. And the EMF across primary we are going to call as EP, and the voltage across primary we are going to call as VP. Okay, simple to understand. Then secondary coil in secondary coil the number of turns is given by NS, the EMF is given by ES, which will be the induced EMF, and the voltage will be given by VS. Now one thing to remember, the voltage across the primary will be similar to the EMF across the primary. Of course, again this is an approximation, and we have to take that approximation to make our formulae be correct. Otherwise, we will have to put in the other factors. We don't want to do that. There are some changes, but to some approximation, we can assume that EP is equal to VP and ES is equal to VS. So remember this when we go forward. Let us begin our derivation now. So some alternating current is passing in the primary, due to which there is induced EMF in the secondary. In the secondary, the induced EMF ES will be given by, ES will be equal to minus NS d phi by dt. Correct? Let us call this first equation. Of course, as we said, this ES will be equal to VS. Okay. Now because of this flux, there is going to be induced EMF in the primary coil as well. Okay, because there is going to be an alternating current that will go through S. So we are going to get some induced EMF in primary coil also, which will be given by EP, which is equal to minus NB d phi by dt. Let us call this equation number second. Okay. Now we can transform equation number 1 and 2 as Vs equal to minus Ns d phi by dt and Vp equal to minus Np d phi by dt. As we said, why we can do that? We are assuming that the EMF across the coils is same as the potential differences. So we get equation number 3 and equation number 4. So we get Vs is equal to minus Ns d phi by dt, Vp is equal to minus Np d phi by dt. And if you divide this equation, let us call this equation 3 by equation number 4, you will get Vs by Vp is equal to Ns by Np. So now note down this relation, we are going to see what it means. So here is what we found out. We found out that Vs, voltage across secondary, divided by Vp, voltage across primary, is equal to Ns, number of turns in secondary, divided by Np, number of turns in the primary. Now, what are the things that we can understand from this? So we can write it like this. we can write Vs is equal to Ns by Np multiplied by Vp. So what it means, the relationship between the secondary voltage and primary voltage is given by this. If let us say the number of turns in the secondary is larger than the number of turns in the primary. Okay, let us take a very simple example. Let us say in the secondary you are having 100 turns and the primary you are having only 50 turns. Okay, so what will be the relation be? Then you will get Ns is equal to Ns by Np, that is 2. Correct? 100 by 50. So you will get Vs is equal to 2 times Vp. Means if your primary voltage let us say is 100 volt. Okay, if primary voltage is 100 volt, then 100 into 200, secondary volt will be 200 volts. Right? If such a thing is happening, that is called as a step up transformer. So here is the meaning that you are in the primary coil, you are sending a certain voltage. Okay, let us say 100 volts. But in the secondary coil, the induced voltage you get is actually twice of that, which is 200 volts. So you can increase the voltage simply by increasing the number of coils in the secondary. And of course, converse is also true. That is, if in the secondary we are having lower number of turns, let us say in the secondary we have 100 turns, but in the primary we are having 200 turns. Okay, so now it will be half, right? So now here you will get Vs is equal to 1/2 of Vp. So if the primary voltage is 100, the secondary voltage will be 50. Okay, so you can, that is called as a step down transformer. Okay, I hope this distinction is clear. So if we are increasing the secondary voltage, step up transformer. If we are decreasing the secondary voltage, that is a step down transformer. Now we can see that if more turns are there of secondary, the voltage is more. But what will happen to the current? Let us find out. To find the relation for current, we will use the formula VPIP is equal to VSIS. Now, and how we are getting this? Basically, this formula for power. There will be no dissipation of power. That is what we are assuming basically. So, power in the primary is equal to power in the secondary. Power, of course, voltage into current. So, we assume power in primary equals power in secondary. So, what is the relation you will get? You will get the relation IP upon IS is equal to Vs upon Vp, which will be equal to Ns upon Np, or we can write this as IP, current in primary divided by Is, current in secondary, is equal to number of turns of secondary upon number of turns of primary. Okay, or let us rearrange this equation and write it as Is is equal to Np upon Ns multiplied by IP. Okay, now here you will see the situation is different. Here you see the number of turns of secondary has gone in the denominator. So now what will happen is, if there are more turns in the secondary, the current will get reduced. Okay, getting the idea? So if let us say in our secondary we are having a step up transformer where the secondary turns are more. So voltage will get doubled. But what will happen to the current? The current will become half. Getting it? So you can increase voltage, but then your output current that you are getting, that current will become less. And in step down transformer, what will happen? The voltage will become less in the secondary, but the current will become more. Of course, to imagine this is a little strange for us, because normally our understanding is voltage bada diya to current badega. Correct? But here different thing is happening, because remember, these are not resistors, these are inductors we are talking about. So in transformers, and of course we are getting induced EMF, that is why such things we are noticing. So remember this, you can increase the voltage of secondary, but by increasing voltage, current will reduce. Okay, or you can decrease the voltage of secondary, and if you decrease voltage, the current will increase. Okay, so this is the relation for transformers. Ensure that you are understanding this concept, and again I will repeat, read the textbook. Now there is one concept that is the power factor, that has been deleted, so I did not teach it in these chapters. It will be there in the class notes that I have given you. Don't bother to write it. Okay, so with that this particular chapter is completed.